My name is Huang Wenjin. I am a PhD student at Shanghai Jiaotong University. In this video, we present Box-FaceS, a simple but effective method that enables flexible face component editing conditioned on component bounding boxes. With its state-of-the-art visual quality and diversity, StyleGAN has recently become the gold standard for image synthesis. Beyond its visual quality, StyleGAN contains a rich latent space, which has been shown to effectively encode semantic information while containing intriguing disentangled properties. Numerous works have leveraged StyleGAN's rich latent representations to perform extensive and diverse image editings, such as ACMMM. Although these methods have achieved impressive results in attribute editing and style transfer, editing a specific face component, such as a single eye, remains a challenging task. This can be partly attributed to the strong correlations between face components. In the widely used face dataset, almost no face has two different eyes. It is difficult for StyleGANs pre-trained on this dataset to learn the concept of a single eye. As a result, most StyleGAN-based methods cannot generate a wink expression, which requires the model to disentangle the left and right eyes. To achieve this, we propose a box-guided component editing method, Box-FaceS, which shows strong component disentanglement. For convenient real image editing, Box-FaceS is built upon the encoder-decoder framework. The encoder is designed as a two-branch architecture to satisfy both accurate reconstruction and high-quality face editing, with one branch capturing image details and the other extracting component embeddings. The two branches share a common subnetwork E. The input face is first passed through the subnetwork E to output a mid-level feature map. Then, the fish icon module downsamples the feature map and outputs a high-dimensional feature tensor called fish icon, which preserves the fished outline information and image details. Meanwhile, the component embedding module learns the component embedding for each fish component based on the feature map and the rescued component bounding boxes. Afterwards, the fish icon S, component embedding C, and the bounding boxes are fed into a style-based generator J to synthesize the final result. On the right is the detailed structure of the generator in Box-FaceS, which is adapted from StyleGAN 2. As shown on the left, StyleGAN 2 expands resolutions from a constant tensor C1 and uses an MLP network to generate intermediate latent codes W. The latent code will further predict a style code to modulate its convolutional layer in a channel-wise manner. The modulation operation is denoted as mod in the left figure. Unlike StyleGAN 2, the generator in Box-FaceS starts from the fish icon S, and the latent space is decomposed into several subspaces, where each subspace corresponds to a specific face component. To enable box-guided face component editing, a box adaptive modulation BAM is designed. We replace the global modulation in StyleGAN 2 with BAM in every layer of the generator. Compared with the global modulation, the proposed BAM allows different regions of the feature map controlled by different style codes and plays a key role in component editing. The box adaptive modulation can adaptively modulate visual styles within box-like regions on the feature maps according to the style codes predicted from component embeddings. The right figure shows the details of BAM. The component embedding Zi are first transformed into component-specific style parameters sigma I by linear projection. Then, the style code will broadcast to their corresponding regions according to the rescued bounding boxes to yield a modulated feature map. The modulated feature maps will be passed through the following convolutional layers. With the BAM, it is flexible to determine the component style by its embedding and to control its position and size by the provided bounding boxes. If the network is tuned in a native way, the face icon branch would compete with the component embedding branch to capture the component features, which will degrade the component editing performance. To avoid this, we propose a cooperative learning strategy to train the network. The input face is perturbed with different masks for different branches. Mask 1 and Mask 2 are independently generated following the shape random irregular mask generation algorithm. Then, Mask 1, which perturbs the input for the face icon branch, further masks out the areas of some face component. By doing so, the face icon branch cannot see the content of certain face components, which encourages face component features to be encoded into the component embeddings rather than the face icon. The overall loss function is similar to StyleGAN 2. We add a reconstruction loss to screen the difference between the output and the input images. Next, we will show some face editing results of our method. In this example, we show the results of face component editing. As shown, Box-FaceS shows strong spatial disentanglement. By translating or scaling the input bounding boxes, Box-FaceS can successfully change the positions or sizes of face components while maintaining the high quality of generated faces. With flexible component editing, Box-FaceS can create some interesting faces that do not exist in the dataset. In this example, we show the results of face component transfer. We manipulate the target face by transferring the component embeddings from a reference face. As shown, the shape and texture of the face component can be accurately transferred and naturally fused with the target faces. In this example, we apply Box-FaceS trained on real faces to non-real face editing without any retuning or fine-tuning. The pre-trained Box-FaceS can generalize well to artistic portraits, sculptures, and cartoon faces, demonstrating the robustness of Box-FaceS to various face styles. Our model can also be adapted to other domains where the components are defined as animals in natural scenes. The results show that Box-FaceS not only has the flexibility to change the position, size, and shape of individual animals, but also supports the removal or addition of animals in the natural scenes. At the end of this video, we would like to discuss the potential applications of the proposed method. By changing the relative position and size of face components, users can generate some interesting faces with our method, which can boost their imaginations. Besides, Box-FaceS can generate high-quality out-of-distribution samples, such as faces with wink expressions or long eye distance. These out-of-distribution face samples can be further used to augment the training dataset for some downstream tasks, such as face segmentation, to improve the robustness of the models on out-of-distribution samples. Thank you for watching this video, and you are welcome to check our paper for more details.